Hello everyone, welcome again to this channel. This is G Solutions, where we present solutions for your needs. Now let us discuss phasors. This is very important in our circuit analysis since that current is in consideration and it has a direction. When we speak of the direction and the magnitude, we need a vector quantity for that. These two quantities also can be merged into a single expression to facilitate the use of this vector in equations. So our representation is this one. This is the magnitude and this is the theta, the angle of direction. So you have here an angle. We can better understand this in this drawing. You'll notice that A here is the hypotenuse and our theta here is the angle here. And you know that this A, which is the hypotenuse, is having a components, which is the vertical components, AY, and the horizontal components, AX. Knowing AX and AY would enable us to get the vector in its polar form. So we can write actually this vector, AX and AY, into this form. Okay, so AX plus AY, in which this is the horizontal, the vertical, so you place here J. Okay, by the way, J or I, you can use I or J or I. Okay, it is postulated that this is equivalent to the square root of -1. If you have I squared, you will have -1 because that is square root of -1 times square root of -1. I cubed, you multiply I squared to I, so that will be -I, or the negative of the square root of -1. And for your i's raised to the 4, this is equal to 1. That's the value of our representation, letter J or I. We can actually change a polar to rectangular. And if you have an AX, this is from polar to rectangular form. It's very important. So your AX is actually based here. By using the cosine law, you just take the adjacent over the hypotenuse. So actually this is a cosine theta. So you apply here the cosine law. And for AY, we apply the sine law, that is the opposite. This is the angle opposite of that over the hypotenuse. So this will be A times sine theta. So this is from polar to rectangular. You can also change this one to angular form to polar form, which is the polar components. We know that A is actually equal to here, the rectangular components A. This is a right triangle. So you have here 90 degree. So this is your vertical and the horizontal. To be able to get the hypotenuse, we know that that is A. By the Pythagorean theorem, we have AX squared plus AY squared. Okay? And our theta can be computed as the tangent inverse, or the inverse tangent of AY over AX, because tangent theta is opposite over the adjacent. So if you're going to get the angle, you just get the inverse tangent of that. This is very important in our circuit analysis. So the polar and rectangular forms of a voltage is represented by this. So this is the polar form. Okay, if you have the voltage, if you are using, for instance, the voltage, you say P angle theta. Okay, or we can call this as CIS. This is an acronym for cosine as I sine. You're just using a trigonometric function. So we can read this as V cis of theta. It means that this V is multiplied to the cosine of theta plus I times V times sine of theta. Let's distribute V to cosine theta and V to sine theta. Okay, that's why we call this as B cis of theta. So this is the phasor representation. And if you are going to get the rectangular form for that, this is just represented as B sub X plus J V sub Y. More so, we can also show from the so-called Maclaurin's series expansion of the sine cosine exponential functions, that our E, j theta is equals to cosine theta plus j sine theta. So your A here again is equals to the root of -1. Therefore, we can have this representation that ej theta is actually 1 cis of theta. That's it. Thank you.